In this session we're going to talk about scientific thinking. In fact, this type of thinking is logical thinking, and it's applicable in the context of business research, sociological research, as well as academic research. So scientific thinking is really logical thinking, and that's why it's included in these series of classes on business. So let's look at what we mean by scientific thinking. First of all, let's look at the essential characteristics of a science. Well, a science starts with postulating or asserting a relationship between two or more variables. So the variables could be if two chemicals are combined, the consequence will be a certain reaction. Or it could be something in business. It could be a cut in price will generate more sales. It's a scientific statement. It's a very positive statement. It's saying that if the price of a product is reduced, there will be more sales. It's postulating a relationship between price and sales. The same as a scientist, a chemist, for example, may say if two chemicals are mixed, there will be a certain reaction. It's postulating that there will be a reaction. It's stating strongly that there will be a reaction. So we're using this idea of variables and relationships all the time. We're using it in business. There is a variable, price, and there is the number of items sold. That's a variable. And we're postulating a relationship between the two. With science, we have, generally speaking, we have observations of phenomena. We try to collect relevant data. We try to make observations and collect relevant data. And we have very clearly defined variables and methods and procedures. Everything is set out. There's no secret agenda. We know what the variables are. Let's say in the context of business, I mentioned earlier, we have the price. Well, that's a variable. That's clear. The number of items sold. That's clear. That's quantitative as well. The method, where we have to link the two together, and we would use some sort of statistical approach to try and determine what's the relationship between the two of them. So we have a procedure. We have a method and a procedure to follow. We say they're empirically testable. The hypotheses are empirically testable. Now, a hypothesis is just a testable statement. Any statement which is testable. So I could say there is a very strong relationship between the price of the product and the number of items sold. That's my hypothesis. That's my testable statement. Some statements are not testable. Today is a beautiful day. Well, that's my opinion of today. Your opinion of today could be it's a terrible day. It's cold and terrible. My opinion is it's nice. We can't test. It's just two opinions here. So a testable hypothesis is one that can be tested. Empirically means done by experiment. Nowadays we use the word empirically differently. We use the word it's a practical test. Normally it's a statistical test between relationships, two variables. So the price of the product and the number of items sold. We test it empirically. We test the data to see if there is such a relationship. That's what we mean by empirically. It's a practical calculation to see if there is a relationship. Now, hypotheses, and you'll note the spelling here is slightly different. Move from hypothesis is one, I-S, H-Y-P-O-T-H-E-S-I-S is a single one, single hypothesis, and hypotheses ES at the end. These are a number of hypotheses. Now, hypotheses may be accepted or rejected. So we may accept that there is a strong relationship between price and quantity sold, or we may reject it. Generally speaking, we use a lot of statistical analysis to try and work out whether a hypothesis is accepted or rejected. So that is the role for statistics. If it's rejected, then we may go through the process again and get a different hypothesis and test it as well. So we go through a process of correcting hypotheses until we find some that do describe the situation. So in the case I mentioned earlier of the price being a big determinant of sales, well, it may be, or it may be that income levels in the area are very important. That if the price is reduced, sales may not increase because people in the area don't have incomes, don't have big incomes to afford the product. So even though the product is cheaper, no extra sales are being produced as a consequence. So we need to go through iteration of the hypothesis to try and find what is going on. Now, ways to communicate. Well, first of all, we have the exposition. The exposition is our statement. So we have an exposition, we describe what we're trying to do, and we make descriptive statements about what we're trying to do, what the relationships are, and why we believe these relationships to be true, and how we're going to set about doing the analysis. This is our exposition. Our exposition is a statement of what we believe to be correct and how we're going to look at it. An argument is a particular statement that we're going to test. An argument in a discussion is a statement that can be tested. So an argument is what enables us to interpret and to defend and challenge and explore meaning. So we put forward an argument in the case, we put forward a particular statement, and then we try to defend the statement. In everyday language, an argument is usually something which is not very nice. It involves people disagreeing with each other and just an area of disagreement. But in science, and the way we're talking about it, an argument is a position. It's a relationship that's stated between variables. In my case, let's say I say my argument is that the price of the product determines the sales. That's my argument. Now you may disagree. You may say, oh no, income levels are important. I say, okay, we need to test this. We need to get some facts and figures and do some analysis. So we're challenging the arguments. Now the importance of arguments in research, well, we have deduction reasons from the general to the particular. So if I said every time the price of the product is reduced, there has been more sales. Every time the price is reduced, more sales has resulted. That's every time. Every time means that's general, that every time it happens. Now, the company has just reduced the price of the product, therefore there will be more sales. I am using deduction. I'm going from the general to the particular. I'm going from the general to the particular of what happens right now. The opposite is induction. We look at particular facts. We say the company, I should say. The company has just cut the price of the product and it's selling more because of that. Now, this happened before. What happened the last time it cut the price of the product? Did it sell more as well? And the time before that? Now, if it happens every time, we may come up with the conclusion, we may induce the conclusion that every time it cuts the price, it generates more sales. We have induced. We've looked at particular facts, and if all the facts suggest the same thing, then we induce some general statement. Every time the company cuts the price of the product, it gets more sales. Every time. That's the general statement. And we got the general statement by induction. Now, the building blocks of theory. Well, first of all, we have concepts. Then we have something called constructs. We have definitions. We'll talk about these later. We have variables. We have propositions or hypotheses. We have theories, models. So we have a whole variety of different building blocks. So let's look at some of these. Let's start with concepts. A concept is a set of characteristics associated with certain events. A set of characteristics. That's the concept. It's the concept or the idea. Concepts have been developed over time through shared usage. So we have the concept of a house, because we all understand what a house to be. It's where we live, or where people live. It's a concept. The concept of the house is different from the house. The house is the actual physical building, but the concept is what enables us to talk about the house. So I could say there is a house near me, and you will understand that a house is where people live. I'm not telling you the shape of the house or the color of the house or the size of the house, and yet you understand what I mean. You understand it's a house. So you have a concept. And you have that concept because we have shared usage of the word. The success of research hinges on how clearly we conceptualize, how clearly we understand the different phenomena, and how well others understand the concepts we use. If we use different concepts, if we use concepts of relationship, for example, the price of the product influenced the sales of the product. Now I have this concept that as the price falls, more will be sold. So my concept of the market involves that relationship. Now, others must understand what I mean by the market and price reduction and more sales. They must have ideas that are able to link together in order for us to have common concepts. So we're able to move forward. We're able to conduct analysis. So we conceptualize by thinking about ideas, thinking about products or relationships, and we conceptualize, which enables us to have meaningful discussions. Now, I mentioned earlier this idea of a construct. Well, it's an image or an idea specifically invented for a given research purpose. So it's an idea that has been invented for a particular research purpose. It's composed of concepts. A construct is It's like a set of concepts brought together that is going to be tested. So the construct is the relationship between concepts that can be tested. It's at a very theoretical level. The construct is the set of ideas that are going to be tested. The set of ideas, these are concepts of relationships or concepts of products that we all clearly understand. So once we have a clear understanding of the concepts, we link them together to form the construct. And this is at a very theoretical level, but this is what we can test. This is the idea that we can test. Types of variables. Well, there are many types of variables. For example, here I've got y, which is called the dependent variable because it depends on the value of x. X is the independent variable. So I've written it as y equals function x. F means function in mathematics. It means, in this case, there is a relationship between x and y. I don't know what the relationship is because I don't know what f is. It's just a function. That's called an implicit function because I don't know what the relationship is. If I did know the relationship, if I knew that y equals 2x squared plus 3, that's called an explicit function. Explicit because I know exactly what the relationship between the two variables is. So we're posing a relationship between two situations. The example I used earlier was a fall in price generates more sales. A fall in price is a variable. More sales is a variable. In that case, I'm saying more sales depends on the fall in price. So I have an independent and a dependent variable, the same as I've got on the screen at the moment. There are many types of variable, and I've included a PDF in the class notes from the University of Indiana, I think, which just simply discusses many different types of variable, which you can have a look at. Now, let's look at the role of hypotheses. A hypothesis is a testable statement. It's a statement that can be tested. As I said to you, if I said today is a beautiful day, it's not testable. If I define what I mean by a beautiful day, it could be testable. If I said a beautiful day is when the temperature is between 22 and 25 degrees centigrade. Now we can test the temperature today, and if it falls in that range, it's a beautiful day. So it could be testable if I specified. When a hypothesis is tested many times, it becomes a theory. So if we test a hypothesis many times, then we may generate a theory. Let's go back to my example again. Fall in price generates more sales. That's my hypothesis. I'm saying a fall in price is the cause of more sales. So I get some data on reduction in price, some data on increased sales or on sales in general, and see if they've gone up or if gone down or whatever. And I test my hypothesis. Now if I test it many times, I start to come towards a theory. My theory is every time price falls, more sales will result. That's my theory. I've got the theory because I've tested the hypothesis many times. Now the benefits of posing a hypothesis are as follows. It gives focus to the work. And this is the center of the investigation. So it's important to have a hypothesis because that's what's going to be tested. Without the hypothesis, there is no testing. It provides clarity and is either accepted or rejected by analysis of the data. So the hypothesis is a clear statement, and when it's tested against the data, it's either accepted or it's rejected. Very clear. It helps to select the appropriate data and reject the rest. So the hypothesis tells the researcher what data is necessary. Go back to my example. A fall in price leads to more sales. So what the researcher needs is data on price variation and data on sales variations. So those are the only two pieces of data that the researcher needs. In fact, the researcher will probably take other related data like changes in incomes in the area and seasonal factors and so on into account to try and work out what the true relationship is. But the essential pieces of information are information on changes in price and changes in sales. So it helps the researcher to focus. The nature of the hypothesis is an indication of the type of research method that is required. The one go back to it again, the one I've just mentioned, variations in price leading to variations in sales, that's quantitative. We can measure changes in price and we can measure changes in sales. So a statistical method. Perhaps it's a linear relationship, so it might be regression, or at least a correlation coefficient to show what sort of association there is between the data. So the hypothesis may suggest particular research approaches that could be adopted. Now there are good and bad hypotheses. Generally, a good hypothesis should fulfill three conditions. A good hypothesis should be clear and precise. The one I had was a good one. A change in price leads to a change in sales. That's clear. It's very precise as well. It must be testable. Well, my hypothesis just now was testable. Get the data, test it. So it must be testable to make it a good hypothesis. And it should be based on a literature, on past research, and add to wider understanding of the area. Well, in my case, my hypothesis was based on the theory of demand in economics, which goes back a long way, perhaps back to Alfred Marshall in 1890 and the principles of economics. But it should be based on the literature. It shouldn't be just a hypothesis that's almost a crazy statement, just made up. It should be based on some sort of reasoning and some sort of logic and some sort of history. It should be something which is reasonable to suggest, not just some idle speculation. And those are the conditions that make a good hypothesis. Now the value of a theory, well, it focuses the field of study because it's a theory in a certain way. And a theory, don't forget, is generated from looking at various hypotheses in the past. It summarizes past research into a statement. So it looks at the outcome of past testing of hypotheses and summarizes all of that into a statement, which becomes the theory. Now, having got a theory, it may be used to try and predict future observations. This is a bit more controversial because it's bordering on witchcraft. It may be true or it may not be true. It's very difficult to see the future. In the natural sciences, generally speaking, we expect them to be more predictable. So if we take I don't know, Boyle's law in physics. Pressure, temperature, and volume for a particular gas. Those are related. If the volume is held constant and the temperature is increased, then the pressure will increase. Now that's based on lots of testing, and that's theory. It's Boyle's law in physics. So physicists would suggest that that will apply anywhere in the universe, and that should apply in 1,000,000 years' time. I'd like to think that my statement about a reduction in price will lead to more sales will apply in 1,000,000 years' time. But somehow I'm less confident. Maybe I should be more confident, but looking into the future is problematic in the social sciences, in business, in sociology and economics and many areas. But in the natural sciences, in physics, in chemistry, in biology, in those areas there's much more predictability. However, a theory is used to make predictions about the future. It's based on inductive logic. Several generalizations are rolled together to form a theory. The generalizations in the sense that it looks at testing hypotheses, it looks at testing the hypothesis over and over and over, testing variations in the hypothesis over and over and over, and rolling all of this together to induce the theory. And that's what we mean by a theory in science. In this session I've talked about many different but important terms when we talk about scientific thinking. In business and in the social sciences, although many researchers try to copy what happens in the natural sciences, it's difficult because we're dealing with people, and people are not that predictable. We don't like to be predictable for a start. We like to be individuals. We like to be different. So statements in business and in social science are much more circumspect. We have to allow for the probability, for the chance of change. And looking at the same investigation over and over and over doesn't mean getting the same result over and over and over. We may get different results because people are so different. That's all I'm going to do on this topic, so I'm going to leave it at that and say thank you for watching.